Good afternoon, everyone. So I would like to thank Shadab and all the organizers for inviting me in this workshop to present this talk. So I will talk about something related to the assembly bias. So let us start. So we know that the observations tells us that the galaxy properties like luminosity, color, morphology, star formation rate, stellar mass, and metallicity strongly depends on the local density of their environment. A number of known physical mechanisms and quenching processes are believed to be responsible for such environmental dependence. One of the, I think the morphology density relation is perhaps the most well-known example of the environmental dependence of galaxy properties. And I'm mentioning this because I'll be primarily focusing on the possible correlation of galaxy morphology with the large-scale environment in this talk. Now, why bother about the large-scale environment? Now, there is a growing body of evidence that the properties of galaxies and their host dark matter halos are influenced by the large-scale tidal environment, assembly bias, and galactic conformity. Now, these effects are somewhat related with each other, but most importantly, they can give rise to large-scale environmental dependence of galaxy property. Measuring the strength of these effects and comparing them with simulations can provide us important information about the impact of large-scale structures on galaxy formation and evolution. So in this talk, I will discuss about an information theoretic framework which can probe the correlation between any galaxy property and the large-scale environment. So I will discuss about this framework in the next few slides. So in information theory, information entropy of a discrete random variable x is defined by this expression. Here, n is the total number of possible outcomes, and pxi is the probability of the ith outcome. The information entropy quantifies the uncertainty in the knowledge of a random variable. One can also define the mutual information between two different random variable x and y using this relation. Here, hx and hy are individual entropies, and hxy is the entropy corresponding to the joint probability distribution of x and y. Now, mutual information quantifies the reduction of uncertainty in the knowledge of one random variable, given that we have knowledge of the other. I will refer to mutual information as MI for the rest of my talk. So MI is a measure of statistical dependence between two random variables. And a key advantage of using MI is that it doesn't make any assumption regarding the nature of the random variables and the relationship between them. So one can use MI to probe correlation even when the variables are non-Gaussian and the relationship between the variables are non-linear or non-monotone. So in our method, we need the galaxy distribution in a large cubic region with the morphological information of the galaxy. So we need the galaxy distribution as well as their morphology. We divide this entire region into ND regular voxels of size DH inverse megaparsec and count the number of spirals and ellipticals within each of them. Next, we define two random variables, x and y, with probability distribution px and py. Here, pxi is the probability that a randomly chosen galaxy resides in the ith voxel. And this can be simply given by ni by n, where ni is the number of galaxies, total number of galaxies in the ith voxel, and n, capital N, is the total number of galaxies. Clearly, x has total nd outcomes. Similarly, one can define the probability of y, pyj, is the probability that a randomly chosen galaxy is spiral or elliptical. And y has only two outcomes, and the probability of the first outcome is given by simply the ratio of number of spirals to total number of galaxies in the sample, and py2 similarly is the ratio of total number of ellipticals in our sample divided by the total galaxy. One can also calculate the joint probability that a randomly selected galaxy resides in the ith voxel and it is spiral or elliptical, which is given by Pxy. So Pxy is the product of the conditional probability Py given x and the marginal probability Px. So here Pyx is the conditional probability that the randomly selected galaxy is spiral or elliptical, given that it resides in the ith voxel. One can easily calculate Pxiyj, which will be simply the number of spirals in the ith voxel divided by the total number of galaxies for j equal to 1. And similarly for j equal to 2, it is n number of ellipticals in the ith voxel divided by the total number of galaxies. Once we have this probability distribution, one can calculate the joint entropy. So joint entropy Hxy is simply can be calculated by using this expression, where Pxiyj is the joint probability of x and y. And once we have Px, Py, and Pxy, we can calculate the mutual information. So mutual information can be also understood as the relative entropy between the joint probability distribution of the two random variables and the product of their marginal distribution. And one can, after a few lines of algebra, one can show that this first line will reduce to the second line, which we have shown earlier. So since we have already calculated this entropy for x, y, and the joint entropy xy, so one can easily calculate the mutual information between x and y. And since entropy quantifies uncertainty, so hxy will be always smaller than hx plus hy, given that there is a correlation between x and y. So mutual information is expected to be positive whenever there is a correlation between x and y. And a mutual information of 0 indicates that the two variables are statistically independent. Now, we apply this framework to calculate the, so one can basically repeat this entire exercise for different grid sites. So, and calculate the mutual information between morphology and environment. So we apply this concept in the data from Sloan survey and Galaxy Zoo project. So Sloan survey is one of the largest redshift survey, which provides us the photometric and spectroscopic information of millions of galaxies. And Galaxy Zoo is a citizen science project which provides us visually classified morphology of more than 1 million galaxies. So this is the sky coverage of our sample. This alpha is right ascension and delta is declination. We construct a volume limited sample by restricting the extinction corrected and K corrected R band absolute magnitude to MR less than -20. And this provides us a volume limited sample, which extends up to a redshift of 0.1 and consists of 42,334 galaxies, which have morphological information available from Galaxy Zoo. And we only considered the galaxies for which the morphology is classified with a de-biased Vogt fraction greater than 0.8. This is to increase the reliability of the classification. And then we carve out the largest cubic region that can fit within our volume limited sample. And this cube has a side of 160 H inverse megaparsec. The data cube contains a total 15,860 galaxies, out of which 11,875 are spirals and 3,985 are ellipticals. We calculate the mutual information for this data set for different grid size and show this in this plot. So one can see that there is a small but non-zero mutual information between morphology and environment that decreases with increasing length scale, but persists throughout the entire length scale that we have probed in our analysis. Now the question is, how do we know that these signals have any physical significance? In order to, one can argue that such kind of small mutual information may arise due to the finite and discrete nature of the distribution. In order to test that, first we construct a set of mock catalogs from a semi-analytic model implemented in the Millennium Run simulation. So the goal is to simulate the morphology density relation and try to test whether the this MI between morphology and environment are significantly different in the presence of a morphology density relation and in absence of it. So what I do, we construct a set of mock catalog from the Millennium simulation, a semi-analytic model of Millennium simulation, and then calculate the density at the location of each mock galaxy using a kth neighbor method. We use 3 different schemes to identify ellipticals and spirals. So these boxes show you the distribution of ellipticals and spirals in 3 different schemes. So the brown dots represent the position of ellipticals and the green ones show the position of spirals. In the first scheme, the top left side, we tag galaxies as elliptical from the top 30% densest region in the box. And here we keep the ratio of the spiral and elliptical same as the original data. So same number of elliptical and spirals should be there in the mock data as they were in the original data. In the second scheme, we select or tag galaxies as elliptical from the top 50% galaxies in the densest region. And in the third one, we tag galaxies as elliptical from the entire box, irrespective of the density at their location. So clearly, there is a stronger morphology density correlation in the first scheme. This morphology density relation is somewhat weaker in the second one, and there is no density morphology correlation at all in the third one. We calculate the MI once again for these 3 cases and show it here. The left-hand side plot shows you the mutual information as a function of the grid size for these 3 schemes. So the black curve or the black circles are for the data set where we do not implement any morphology density relation, whereas the green one is for the case where ellipticals were chosen from the top 50% densest region, and the bluer one is from the case where we chose ellipticals from the top 30% densest region. We also repeat our exercise in a Poisson random catalog, where again morphology is assigned randomly, and this is shown with a red triangle, and we see this red and the black one is completely overlapping with each other. So we can clearly see that the Millennium data and Poisson data, they give exactly same result when there is no morphology density correlation. But when we have some amount of morphology density correlation, we can see that those cases are clearly different with the random data sets. In order to test the statistical significance of these differences, we carry out a t-test. The results are shown on the right-hand side. So this horizontal line is the critical t-score corresponding to 99.9% confidence level. So we test the differences between this green curve and the black curve and the blue and the black curve. And we find that there is strong evidence against the null hypothesis at each and every length scale that we have analyzed here. Now, this is just a test with a mock catalog to show that MI can effectively capture the degree of association between morphology and environment. But how do we know that the signal that we have captured in the SDSS data is something physical or it's a spurious signal? In order to test this, we conduct 2 experiments here. So I'm describing both of them one by one. So here, what we do is that this red curve is for the original SDSS data. And keeping the number of spirals ellipticals same, we randomize the morphological information in the original data. So we would expect that this would destroy any existing physical correlation between morphology and environment. So if these correlations are physical, we expect a reduction in the mutual information at a given length scale. So we see that there is indeed a reduction in the MI when we randomize the morphological information. Again, we carry out a similar test with Poisson data, and we see that the Poisson data and SDSS data, SDSS randomized data, do not have any difference at all. Since this blue and this black data points are nearly overlapping with each other. But there's a clear difference between the red one and this black and blue one. Again, we test the statistical significance of these differences using a t-test. The results are shown on the right-hand side. And this is the critical t-score for this 99 for this test for 99.9% confidence level. And we can see that these differences can be, this null hypothesis can be rejected at a very high confidence level for each of the data points. Now, one can also destroy the mutual information between morphology and environment by shuffling the galaxy distribution while keeping the morphological information intact. We achieve this by using a statistical technique called shuffle. So what is shuffle? Let me describe it. This cubic box on the top left shows you the actual galaxy distribution. Here, this purple dots are ellipticals and cyan dots are spirals. So we divide, this is the unshuffled data, actual original data. We divide this entire cube into a number of regular subcubes and then randomly rotate each of these subcubes around any of the three axes by an angle which is integral multiple of 90 degrees, and then randomly swap their position, interchange their position. So this is done many times in order to generate a shuffled distribution. So this process is expected to destroy all the coherent structure which are larger than the size of the subcubes, whereas it will leave all the smaller structures nearly intact. So one can basically choose the different size of the shuffling unit. For this case, ns equal to 3. So we have 3 to the power 3, total 27 subcubes. And in the bottom left one, we have ns equal to 7, so 7 to the power 3, total 343 subcubes. And the bottom right, we have 15 to the power cube, so total 3,370 subcubes. So basically, when you shuffle the data using a particular shuffling unit of a given size, we are destroying all the coherent features in the data above that size. So this will destroy any existing physical correlation between morphology and environment in the actual data, if they are physical at all. So we expect a reduction in the mutual information if they are physical. So let us see the results. So this shows you the results. Again, the red one is for the actual unshuffled data, and the bottom one is for the Poisson data, which is basically featureless thing and randomized basically without shuffling. And the three curves in between the red and black one are for 3 different shuffling lengths. So you can see that there is a systematic reduction in the mutual information at different length scales. As we decrease the shuffling unit or the size of the subcubes, more and more structures are getting destroyed and the mutual information is removed from the data. So you see a systematic reduction, and we test the statistical significance of the differences again using a t-test, where this horizontal black line shows you basically the critical t-score corresponding to 99.9% confidence level. We see that the null hypothesis can be rejected at most of the grid side, and we see that there is a weak evidence against the null hypothesis at the smallest values of the grid side, and that is because shuffling leaves the smaller structures nearly intact for all these 3 different shuffling unit that we have chosen for our analysis. So basically, we see from these tests that there is a small but statistically significant mutual information between morphology and environment that persists throughout the entire length scale that we have probed in our analysis. Now, the next question would be, how do we know that this is assembly bias or something else? So we have to basically explore further to understand the physical origin of these signals. So what we did, that immediately that comes to our mind that maybe the stellar mass may have some role, because stellar mass function depends both on morphology and environment. So the link between stellar mass and morphology and environment may possibly explain this non-zero MI that we are measuring in the data. So what we did is basically we measured the conditional mutual information. So conditional mutual information is basically the mutual information between morphology and environment by conditioning the stellar mass. One can so CMI basically provides us the expected value of the MI between 2 random variables when we have complete knowledge about the third random variable Z. In this case, Z is the stellar mass. So this is the definition of conditional mutual information, and one can again calculate these quantities, these joint entropies between XZ, YZ, and XYZ simply from the data. This is the joint entropy of XYZ, which can be easily calculated using Bayes formula. And if you calculate this and get a value 0, that implies that X is independent of Y. That means there is no correlation between X and Y. The observed non-zero MI is simply due to their correlation with the stellar mass or Z. But in reality, this is an ideal case. In reality, we have seen that even in a randomized data set, we have a non-zero small MI. So our definition should be that if we measure the mutual information between morphology and environment by conditioning the stellar mass, and it reduces to the MI observed in the random data set, then we can conclude that this observed MI between X and Y is purely a consequence between the correlation between X and Z and Y and Z. So Z is correlated with both X and Y and giving rise to such non-zero mutual information. But that is not the case. We calculated this CMI, so the conditional mutual information between X, Y, and Z for the actual data. The red curve is for the actual data. The bottommost curve, these cyan triangles are for the randomized data set. And in between there, we have also calculated this for 3 different semi-analytic models from the Millennium simulation. And we find that clearly the CMI in the observed data doesn't reduce to the MI observed in the this randomized data set, which clearly indicates also similar is the case for the semi-analytic models which we've tried here. And the differences had several implications, which I am not going to discuss because of the time constraint here. And so basically this result tells us that environment and morphology dependence of stellar mass are not sufficient in explaining the observed MI between morphology and environment at different length scale. So what could be the other possibilities? We look for another possible explanation. So here we have measured the mutual information between the environment on different length scale. So we are dividing the data cube into voxels of different size. So when we are dividing it into a voxel size, say D1 and D2, we can measure the mutual information between our measurement. So basically X bar is basically another length scale, and D1 and D2 are 2 different grid size. So one can again calculate the joint entropy HX bar simply by calculating the joint probability PXI bar, which is nothing but NIKYN, where NIK is the number of galaxies shared by the ith voxel of grid size D1 and kth voxel of grid size D2. So once we know this PXI bar, we can easily calculate the joint entropy HX bar. And let me show you the results. So this diagram shows you the mutual information between the environment on different length scales. So X and X bar are shown along X and Y axis. So each pixel shows you the mutual information between a pair of different grid size or length scale, which we measure from the data. Now this result tells us that the MI between X and X bar again decreases with increasing length scale, but the MI between X and X bar are much higher as compared to the MI between X and Y, that is environment and morphology. You can clearly see that the MI between X and X bar is almost 2 orders of magnitude larger than the mutual information that we have measured for X and Y. So if X and Y have some mutual information on smaller scale, this can translate to a mutual information between X bar and Y on larger length scale. And this could possibly explain the mutual information that we are observing on larger length scale. Now, we expect that this mutual information between different length scale would be sensitive to tidal environment and assembly bias. And we are yet to explore these issues.
Biswajit?
Yeah. I'll stop.
Reminder.
Yeah.
Just a time.
I'm almost done. Yeah.
We're into the question and answer session.
Okay. Okay.
That's fine.
Please. Should I proceed?
Well, you should try to wind it down. Sorry.
Yeah. I'm almost finished. This is the last slide. Yeah. So we applied this same concept to a number of different problems in cosmology. So we tried to see whether the angular momentum of dark matter halos correlates with the large scale environment. And again, we find that for massive halos, we find a small but statistically significant correlation with their large scale environment. We know that the significant number of spirals show red colors, and the region is still not clear. So we tried to see whether the color of spiral galaxies had some correlation with their large scale environment. And we again find a small but statistically significant MI with their of color with the large scale environment. We also test if the presence of galactic bars in spirals depends on the large scale environment. And we do not find any statistically significant evidence in favor of it. So as my previous speaker mentioned, that the assembly bias is a robust prediction of lambda CDM model, and it is important to find observational evidence of it. And we believe that this information theoretic framework can serve as a sensitive probe of the assembly bias. So I thank my collaborators Suman Sarkar and Snehasis Bhattacharya who were involved in this project. And I acknowledge the SDSS team and Galaxy Zoo team for making the data public, and thank DST for providing support through these two projects. Thanks for your attention.
Thanks very much. Okay, thanks for the nice talk. Very interesting result. The long scale, the morphology correlation with very large length scales. Any questions? Please.
Thanks, Biswajit. I think you're showing this result from SDSS and comparing that with GAL form simulation.
No, our comparison was with 3 different semi-analytic models from the Millennium simulation.
All right, yeah, sorry, different. So the semi-analytical model and things are not matching. Could you think about like maybe this is limitation of the semi-analytical model because of that?
Yeah, so one consequence of these differences would be that this correlation between morphology and stellar mass. So I mean, the change in morphology, I mean, the differences that indicate that the change in morphology does not necessarily indicate a change in stellar mass, and vice versa. So what are the physical processes that can give rise to such events that has to be investigated? And further, we have seen that on larger scale, the results from the simulation, if you see the larger, I mean, they quite match with the random data set. But in case of SDSS data, we saw that a small but significant MI persists throughout the entire length scale. So that is something inconsistent with this semi-analytic models.
Okay, thanks again, Biswajit.
Thank you. Thank you.
Pause.